So I already said what is called sampling. So to convert a continuous time in discrete, to convert a continuous time signal into a discrete time signal, the process is called sampling. Okay. So why it's required to study? Because what happened when we do a sample, what are the frequency component present in the sampled version of the signal that we can uh, say, okay, that we can say by looking the expression, okay, of a signal, of a sample signal. Okay, that's we are going to discuss in this topic, sampling. Okay, there are different types of sampling is there. I have explained in the previous classes that impulse signal has taken. We can take some samples of the signal. Okay, that is one type of sample. There are other types of sample also, like natural sampling or flat top sampling, that we are going to discuss. Okay, in this topic. So first of all, you write the definition of what is called sampling. Sampling is a process used to convert a continuous time signal to a discrete time signal. Okay, that's what we know already. That I am saying that why we need a discrete signal, because computer devices or man-made devices are knows only discrete time signal or digital signal. Okay, that's why this topic is very important. Sampling is a process used to convert continuous time signal to discrete time signal. Okay, it is a process to convert a continuous time signal into discrete time signal. And discrete time signal means we have take some instant of the signal. Okay, the information of the continuous time signal will take the information only for some discrete set of time. So I have said that already that sampling have different methods. Like one is ideal method. Ideal means you can say it is impulse sampling. This is ideal sampling, or you can say this is impulse sampling. Okay, in this case we are use a train of impulse signal to make a continuous time signal into discrete time signal. Then you can say this ideal sampling and practical sampling. Practical sampling mainly two types. One is natural sampling, and there is flat top sampling. Okay, so why it is called ideal sampling or why it is called practical sampling? There is a reason that ideal sampling uses the impulse signal, and I have said that we cannot generate a impulse signal, okay, practically. So but theoretically we can analyze the signal with the taking the impulse concept. But since we cannot generate this ideal sampling practically, so there are two other method which can be generated practically. That's why another type we have categorized as a practical sampling, where one is natural sampling and another is flat top sampling. So have you completed? So these are the different types of sampling. One is ideal sampling, natural sampling, and flat top sampling. And we are going to discuss each of these sampling one by one. Okay. It's over, I think. So if you see the diagram, okay, if you take a continuous time signal, like this, okay.
Sir, once previous slides.
Let me know when you finished.
Sir, completed.
So take a continuous time signal like xt, okay. How we can sample this signal? We have to take a train of impulse signal, okay, or train of impulse signal means these are the impulse signal. The time period of the samples are ts, okay, of the sample signal. These are the train of impulse signal. You can write its delta ts. Ts is the time period of the samples. But when we multiply these two signal, okay, this continuous time signal and this impulse signal, then what will be our output? Only some amplitude values of the continuous time signal from some discrete set of time we will get, okay. When we multiply, suppose this thing, this is the sample signal. Suppose x delta t is a sample signal, which is we have got by multiplying xt with delta ts, okay. Understand? So we are taking some sampled amplitude, and the same impulse signal is gets the amplitude of the continuous time signal when we multiply this train of impulse signal with the continuous time signal, okay. Ts twice ts minus ts minus twice ts, like this, okay. This is the sample signal. But if you look the frequency component, because we are discussing these things to know the frequency component present in the sample signal, okay. That's why we are discussing, taking with the another topic. So if we take the Fourier transform of this, suppose we will get a signal like this, where the frequency components are minus m to omega m, okay. This is the x of omega. This is the Fourier transform of this continuous time signal, okay. Continuous time signal, you know that there will be not a spike we will find. We will find some set of frequency component, okay. Because the frequency is here in this diagram, we have shown that the signal contain the frequency from 0 to omega n, okay. Different frequencies present in this continuous time signal or aperiodic signal, you can say. And the maximum frequency of this signal is nothing but omega m, okay. What will be the frequency Fourier transform of this train of impulse signal? I have given in the previous classes what will be the Fourier transform of the train of impulse signal. Fourier transform of the train of impulse signal is zero omega s. It was a train of impulse signal only, but it takes the amplitude twice pi by ts. Okay, minus omega s minus twice omega s. This will be twice omega s, thrice omega s. Okay, so I have said that when we will multiply in the time domain, what will be the in frequency domain? Frequency domain will be just convolution x of omega convolve with this. Suppose this is delta omega, okay, delta ts omega, then it will be convolve of delta omega. Convolve, when you convolve this signal with this signal, this pattern is shifted to each of the spikes. What I am saying, the representation of the signal will be like this. Suppose this is in the 0. Okay, this is for this is omega m minus omega m to omega m. This is, you can say, omega s. Okay, this is for twice omega s. This is for thrice omega, twice omega s minus. So the it will shift the signal, okay, to left or right side, the same pattern. So like that, we will get the frequency component present in the sample version of the signal. Okay, there will be different types of frequency component present in the sample version of the signal. So this is all this is in terms of graphical representation. And now I am going to give the derivation, okay, and the written derivation to find the mathematical formula for this x of delta omega. Okay, this is the sample version of signal, the frequency component or Fourier transform of the sample version of the signal. So I am going to give the derivation of this process. Please let me know when you finish.
Sir, completed.
Please let me know when you have finished writing. Okay. So let x of t is a band limited signal. What is called band limited signal? Can anybody say? That we are taking xt as a band limited signal. Band limited signal means this signal, okay, this x of t, this x of omega is band limited signal because there has maximum number of frequency component like omega m or minus omega m, okay. So it's not like that their frequency should not be infinity, okay. If their frequency has some fixed number, fixed maximum number, then those signals are band limited. Here we can say that the maximum frequency of this x of omega is omega m. That's why this x of t is band limited. But if you say a string function, okay, if it is going up to infinity, then this is not a band limited signal. The maximum frequency should, we can say, okay, or you can say the maximum frequency present in the signal should be finite. Then that signal are band limited signal. So let xt is a band limited signal and delta ts t is a impulse train signal, okay. So how the what is the time domain equation of impulse train signal or train of impulse signal? That is given by, we know that I have given this formula in the previous classes. The train of impulse signals is represented by summation n equal to minus infinity to infinity delta t minus n ts, okay. So xt is a band limited signal and this is a impulse train, and impulse train equation is given by summation n equal to minus infinity to infinity delta t minus n ts. This is the representation of the delta signal, train of impulse signal. So what is the Fourier transform of this delta signal? That also I have given. The Fourier transform of this thing you should remember. Fourier transform of delta tst is given by delta ts omega equal to 2s pi by ts summation of n equal to minus infinity to infinity delta omega minus n omega s. Okay, this thing you should know, and I have given, I think, to find the Fourier transform of impulse train signal. Okay, I have given in some numerical or in some problems. You can see in the previous classes. Then the train of impulse signal, the Fourier transform is this 2s pi by ts summation n equal to minus infinity to infinity del of omega minus n omega s. Okay. So what is the Fourier transform? What is the sample signal? We have to find the Fourier transform of the sample signal. But what is the time domain representation of the sample signal is Suppose x is delta t. This is a time domain signal of the sample signal, and this is find by, I have already given in the previous pages. We can find the sample signal by multiplying any continuous time signal with train of impulse signal. Okay, delta ts t. When you multiply with train of impulse signal some continuous time signal, that will give the sample version of the signal. Okay, so give it as a one number. Have you completed writing? If we take now Fourier transform in both the sides, because our aim is to find the expression frequency domain representation of sample signal. Okay, then only we can say what are the frequency component present in the signal. That is our main aim, because by time domain we'll know, okay, what will be the representation of the sample signal, but we what will be the frequency component present in the signal, that's we don't know. That's why we have to derive some equation that can say what are the frequency component present in the signal, and I am going to derive that equation. So now we have to take Fourier transform in both the sides. It's over.
Yes, sir.
So now we have to take Fourier transform in both the sides. We'll get what we'll get. So x of d omega will get, okay, and we have to take Fourier transform of multiplication x of t dot delta t as t. Okay, and I have said that if something multiplies there, if you take the Fourier transform, then what will be the output of the Fourier transform? Output will be convolution of these two signal. I have given already. The Fourier transform of multiplication of t signal will be the convolution of this each of the signal, and there will be 1 by twice by multiplication at the initial. Okay, what is the Fourier transform of xt? Fourier transform of xt is x of omega. Okay, convolution, this sign is represented by convolution. What is the convolution of this? Delta t as t. I have given in the equation this. This is the convolution of this delta ts. So I have to write the whole term. This is twice pi by ts delta omega minus n omega s. Okay. So this twice pi cancel. This 1 by ts will come outside. This will be x of omega convolution of summation of n equal to, their summation is there, sorry, the summation is there, n equal to minus infinity to infinity. Okay, minus infinity to infinity delta omega minus n omega s. So also we know that from the properties of delta that is impulse signal, we know that if we convolution some signal with delta t minus t naught, okay, then we'll get x of t minus t naught. Okay, that we know. I have given this property when I discuss in impulse signal, property of impulse signal. There I have given, if we convert some signal with delta signal, okay, then we'll get that this variation, delta variation, come inside the bracket of the x. That is delta t minus t naught will come. So here these things will come in the x term by using this property. Okay, if we convert this signal, then what will be the ultimate output? The summation will come outside. Summation n equal to minus infinity to infinity. The convolution of x omega into delta omega minus omega naught will give x of omega minus n omega s. With the help of this property, this formula, we can say that or x of omega convolution delta omega minus n omega s is capital X omega minus n omega s. Okay, this is x of delta omega. X of delta omega equal to 1 by ts summation n equal to minus infinity to infinity x of omega minus n omega s. Okay, so if you break the signal, if you break the summation part, how it will look like? This is the main equation what I am going to derive. Okay, that omega s, the signal of x omega is shifted version of the signal. Okay, and how much shifted it is? If you put the n equal to 1, 2, 3, then those type of signal will present. Okay, what I am saying, let me write. If you put n equal to minus 1, minus infinity there, okay, let me put n equal to minus 1, then it will be x of omega plus omega s. If you put n equal to 0, then it will be x of omega only. Okay, like if you put n equal to 1, then it will be x of omega minus omega s. Okay, if you look this equation carefully, okay, what is the x of omega? I have given, this is the x of omega, representation of x of omega, this thing. Okay, what will be the x of omega minus omega s? This is the right shifted signal. Okay, in the frequency domain it is shifted to the right. How much shifted? It is omega s. That's why I am given here this thing. It is shifted to the omega s. Okay, like what will be this? This is the left shifted. How much shifted it will be present? Minus omega s. That's why I am given here minus omega s. Okay, this is for minus omega s. If another will come, then this will be twice omega s, like this. Okay, that is, it's go up to infinity because n is present from minus infinity to infinity. Is it clear what I want to say? Because the one signal will be there. There's this message signal, or you can say this x of t, that has a limited frequency minus omega m to omega n. Okay, but if you sampled with the time period omega s, ts, time period ts, and which has the frequency, if you take as a sample frequency is omega s, then that signal is shifted by those frequency only. This omega s, thrice omega s, fourth omega s, like it. Understand? Please let me know when you completed writing. Please join once again, okay? Because Then I will explain, there will be 3 cases, okay, very important cases is there with the help of this omega s, okay. What will be the case if this omega s very small? What will be the case if omega s is very large, okay, with respect to the frequency component of message signal? So that I will explain in the next slide. So there will be 3 cases. One is oversampling, another is perfect sampling, and third number is undersampling. Okay. What will be the graphical representation on this each of the cases I will give in the next pages.